So this is debugging and profiling .NET Core apps on Linux. Very, very specific, but then on the other hand, not a lot of people are doing this yet, and not a lot of people know how to do this yet. A lot of this is still changing and in flux, and hopefully the tools you learn about today will still work in 3 months when you actually have to do this in production. But I have been following this pretty closely, and it looks like there is a story shaping up, so hopefully you'll be able to hear that story. My name is Sasha. I work for a training and consulting company called Sela, and a lot of my work is this, just performance investigations, diagnostics, debugging crashes, core dumps on various systems. Sometimes I do have to go back in time, like last week I was debugging crash dumps of a Visual Basic 6 application, which was not as fun. And then the week after that I could be debugging .NET Core apps on Linux, which is a lot more fun in a way. So it's pretty crazy that we actually got this far, that we are sitting here and seriously talking about debugging and production and investigations of .NET Core on Linux. It did take a while, and it was quite a windy journey, but we got there. And so some of the things I want to show you today are how to profile your .NET Core apps running on Linux without needing a Windows machine in the background for this. We'll talk about visualizing stack traces of CPU samples and also of other things using flame graphs, which are a pretty common tool on Linux and also getting some traction on Windows as well. We'll talk about some other Linux tracing tools like general purpose tracing tools, which happen to work with .NET processes, and they're very important to learn about because that's the tools Linux people just use. We'll talk about runtime events that can be collected, like exceptions, garbage collections, assembly loads, all different kinds of events emitted by the CLR we can collect and then aggregate and do some further analysis on. And we will also talk about core dumps and getting core dumps when our .NET application crashes and how to analyze those core dumps using the tools we have in-box on Linux. Again, like I've said, this is changing pretty quickly, sometimes monthly, sometimes weekly. So again, this sort of works and has been tested with .NET Core 1.1 and .NET Core 2.0 preview. And if it doesn't work next week, it's not my fault as much. And some of this is actually built on top of tools and scripts that I had to hack together a little to get them to work, but it's all in the slides, and hopefully you should be able to replicate these results if you actually need this in production. So just to give a general overview of the equivalents of some of the tools we'll see for Linux on other platforms currently supported by .NET Core. So for CPU sampling, for example, for measuring CPU usage, on Linux, we have PERF. That's what we're going to use mostly. On Windows, we have ETW, event tracing for Windows, and a bunch of tools on top of that. And on macOS, there are also equivalents which use the same idea anyway, if not the same infrastructure. Similarly, tracing, which is basically attaching dynamic logging to your system, is something that can be done on other platforms as well. Dump generation and dump analysis also has equivalent tools. We are going to look only on the Linux side of things in this talk, which let me bring you more demos and more examples. But of course, we could do the same talk on Windows, and we could do the same talk probably for macOS and show similar capabilities anyway, if not exactly the same tools. Now, before we get started, if you actually intend to use my advice in production, if you intend to use any of this in your own production system, you have to mind the overhead. You have to know that production monitoring tools might occasionally have an overhead, which makes them unacceptable for your purposes. So some people here might be okay if you have like a 5% increase in processing time because you use a certain tool, and other people would say, no, 5% is crazy. What are you talking about? You're slowing my system down. So you really have to know what the overhead is, and the best way of knowing is actually testing it in your own environment and seeing the effect. We'll touch on the overhead here and there, but otherwise you have been warned about the overhead. And finally, before we get started with the actual scenarios, just to give a bit of terminology, I'll be using sampling tools and tracing tools in this talk. And I always prefix my talks with a general explanation because this is a little confusing. So basically, sampling means that something is happening so frequently that you can't record every single occurrence of that thing. So for example, if you wanted to trace CPU execution, you couldn't possibly trace every single instruction. It would slow your system down, not by 10%, but probably by a factor of 10,000. So the only thing you can do is sample. Look not at each individual instruction, but every millionth instruction, for example, and then aggregate those samples to form something meaningful. But some events are actually low frequency enough that you can record every single occurrence. Like, for example, disk accesses, or loading of DLLs, or garbage collections. These are things happening infrequently enough that you can actually record every single one, and then look at where they're happening and do some kind of aggregation. So we will use both sampling and tracing tools in this talk for different kinds of events, essentially for different kinds of things we want to trace. So here are some of those things that we might be able to trace and look into. Some of these are coming from the actual .NET Core and the CLR and the .NET Framework, and some of these are coming from the underlying operating system because we are talking again about Linux. So some specifics. If you have a .NET Core app, your .NET Core app could actually, your own code could actually be instrumented with some tracing, with some performance instrumentation. There is a class in the .NET Framework called Event Source, which you can use on Windows to emit ETW events, and you can use it on Linux to emit something similar, runtime events, which you could log and analyze later. So this is one source of information, event source. The CLR itself is instrumented with a bunch of events, both on Windows and Linux, and that includes garbage collections, exceptions, assembly loading, just-in-time compilation. There's several dozens of interesting events that we could trace. On the operating system level, between the kernel and user space, there's a lot of libraries loaded into each .NET application that we could also be tracing using Linux-specific tools, not .NET-specific tools anymore. In the kernel itself, there's a bunch of instrumentation from the scheduler to the network layer to the disk layer, a bunch of things that we could be looking at. Again, OS-specific. There's also events like page faults, migrations between processors, which are emitted by the kernel in a slightly different way, but it doesn't matter a lot for our discussion. And finally, there's hardware events at the lowest level, which are actually coming from your processor's management unit, the performance management unit, and that includes stuff like cache misses and branch mispredictions, interesting things that are not actually OS-specific, but you do have to use an OS-specific tool to capture them and trace them in the context of your .NET application. So let's start with the official story. Like, how are you supposed to do this sort of performance investigation if you look at the official documentation? I'm smiling because it's funny. So the official story is that you go to a website and you download a script called PERF collect. And it's a pretty long bash script, which was written by a performance engineer on the CLR team. And it's fairly isolated and standalone. It's a single bash script which you can use to install all the dependencies you'd need for actually doing performance work on Linux. And perf collect is easy. It's pretty easy to install all the prerequisites. And then you can collect performance information on a running system. Now, the bash script has some command line options, but I'm not covering any of those, and you'll soon understand why. So after you're done with the collection, you have a zip file. And then the story is getting a little murkier. You're supposed to take that zip file, and you can do some analysis locally on Linux, but most of the things you'd want to do require a Windows box. So you need to copy the zip file over to a Windows machine, which is sort of surprising, I suppose. And then you download PerfView, which is an awesome free tool by Microsoft, but it only works on Windows. And then you use PerfView to open that trace.zip file that you recorded, and you can do all your performance analysis there. Now, this is lovely, and it kind of works in most scenarios. Even I'd say it works, but it's not something I could live with for my own production environments. First, there's the turnaround time. You have to create the zip file, copy it over, open it on another machine. And second, I actually like to do my performance work where the data is, where the system is. And just the amount of time I would have to spend to set up this sort of environment with a Windows machine running PERF, for me, makes the whole thing pointless. So this is, again, the official story, and it relies on the same things I am going to be doing manually, but we will actually be doing the investigation on the same Linux system without using Windows-specific tools. Again, it's going to be the same data sources, but in a workflow that hopefully will be a little more reasonable for actual production environments. So the first thing we will use for this is a cool tool called PERF. This is actually built as part of the Linux kernel, so it's available for all Linux distributions. It's not always installed out of the box, but it is part of the kernel tree. So worst case, you can build it from source, or typically you can install it from your distribution's package manager. So once you have PERF installed, it can do both sampling and tracing of various kinds of events, including high-level ones, as well as kernel and hardware events, which are something we'll see a little later. The general architecture of PERF events, of PERF, is something like this. So on the left, on the kernel side, there's the actual PERF events component, which is a kernel mechanism that you can attach to multiple different things happening on your system, to multiple event sources. Most of these event sources are in the kernel as well. For example, you can attach it to functions in the kernel. You can attach it to higher level events like page faults. You can attach it to low level hardware events like cache misses. There's a variety of different sources that you can attach that PERF events runtime to. But you could also attach to user space things, for example, functions in user space libraries. So basically, an arbitrary function in user space can be traced using PERF. And that includes .NET as well to some extent. Now, what PERF can do with those events it aggregates is either write them out to a file, just a big file on disk, which you can analyze offline. You can analyze it later. Or PERF can write the data into a memory-mapped buffer, and then you can have some real-time components, some real-time process, looking at the events in that buffer and just processing them in real time. So if you have very high-frequency events, you probably don't want to dump them out to a file for later analysis because you'll have huge, huge files. So you can instead use the memory-mapped buffer approach. You would still have lots of events to process. It could still probably be quite a high overhead, but at least you're not going to be writing every single thing to disk all the time. We will also see a little later some other alternatives available in modern Linux which make this even more efficient. But this is the general PERF story, and this is also what the PERF collect script is using under the covers. So if you don't think about symbols in advance, and this is the first thing we will have to touch upon, then whenever you use PERF and any associated tools, you will get some pretty useless reports. Like, for example, this report over here is supposed to tell you which functions in your application are spending lots of CPU time. And we will do a demo of this shortly. But the report kind of shows you numbers, addresses, right? Hex numbers and percentages. And these are the actual functions we care about. These are the functions in our own process that should have names, that should have symbolic names. If you're doing this on Windows, a lot of times the tools are taking care of this for you. But in Linux, the whole story is such that you actually have to think about this yourself. So for different kinds of code, there are different sources of symbolic information, which translates numbers, these hex addresses, to function names that you can actually read and use. So there's different colors here for different kinds of code. Here, the dark green is pure managed code, which is just-in-time compiled. So this is plain C#, for example, that you didn't do anything special to. It will be compiled at runtime. And for this kind of code, the symbolic information can be emitted by the CLR into a file at runtime. So you run the application, and the CLR prints out into a separate text file information about code addresses and code function names. I'll show you what that file looks like. It's a very, very simple format. This is, by the way, something you have to do on Windows as well, and it uses ETW to emit this information, but it's pretty much the same story. If you have dynamically generated code, you need at runtime to emit information about code addresses and code function names. Then you have the light green over here. This is still managed code, but it has been compiled ahead of time, AOT compiled. On Windows, NGen is the tool you use for ahead-of-time compilation. On Linux, it's CrossGen, and this is a tool that's actually part of the .NET Core distribution. And you have to run CrossGen on your target machine to get symbolic information for those parts of your application. So for code that's compiled at runtime, you can actually get the runtime to emit the symbolic information. But for code that was compiled ahead of time, you have to do a separate step in order to get debugging information. And it doesn't help that the debugging information CrossGen emits is in a format that no other tool can understand, and you need to write a script to convert it to the right format. But let's leave this behind us. So suppose you have symbolic information for all the managed part of your application. There's still unmanaged code. There's unmanaged code in the CLR itself, which you would need symbols for. And that's something you can typically get by either building from source or by downloading a debug information package for the CLR. And these are available, but not for all distributions. So sometimes you would build from source because that's just the easiest thing. And finally, there's actual operating system binaries for which you also want symbolic information, and that is usually easier to get. So for the kernel, it's typically available online, like part of the running system is symbolic information for the kernel. And for OS libraries, like the C runtime, for example, or the pthreads library, this is something you can get as a package with your distribution. And it's so boring, but unfortunately, you have to get this right. Because if your call stacks from your managed applications are broken at any of these layers, you can't do performance profiling, you can't do tracing, you can't do any meaningful work without function names of your code. So this is something you have to actually get out of the way. And perf collect sort of does this for you. But again, the result can only be analyzed on Windows, which is pretty useless, again, for me. What we are going to do with these stack traces, and this is the last intro part before we actually dive into the demos, what we are going to do with these stack traces of our application that we collect is visualize them using flame graphs. And flame graphs are very useful for displaying a large number of call stacks. So think about call stacks when GCs occur, or call stacks where you access files, or call stacks when you use lots of CPU. You have millions, potentially, of different call stacks that you want to visualize and display to the user at the same time. This is where flame graphs can help. It is basically a very simple visualization approach where each rectangle you see on the diagram is a function. The vertical axis, the y-axis, is just the stack trace. So if a function is on top of something, it was called by that other function. And finally, the horizontal axis is not a timeline. It's just sorted alphabetically. It's pretty simple, and I'll show you a live example of a flame graph coming up. So with all the setup and the introductions out of the way, we can do some CPU profiling. Some of the things I'm going to show you are going to be live demos, and some are going to be pre-cooked screenshots, but let's see just how much time we have exactly. So here I have an Ubuntu box, pretty standard configuration. I did not build my own .NET Core here. I used the standard package of .NET Core 2.0. And I have this buggy application which has a bunch of different issues. And now I think my SSH connection is kind of dropping. Oh, no, it's there. So I'm going to run this thing in fetch mode. This is just one of the things this application can do. It basically is supposed, anyway, to fetch apple.com every once in a while and do something with it, right? The code doesn't really matter. But looking at top, for example, you can see that this buggy process is actually taking like a full CPU core and then some. So it's pretty busy on the CPU, even though it's just supposed to be fetching apple.com off the internet. So something's interesting happening. We're going to use perf to record the behavior of this application and then to analyze it. Before we do that, I want to show you the symbolic information file, which was already emitted when I ran this command. So it's just part of the execution of the CLR. If we look in the temp folder, I have a bunch of those perf info map files and a bunch of perf map files. These perf map files are generated by the CLR and contain symbolic information for that specific process ID. So if we just look at perf pidofbuggy.map, this is the map file for my process. Here's what it contains. It's a super simple, stupid format, code address, code size, function name. Code address, code size, function name. In text format, plain and simple. Now, this is generated in order for us to be able to actually give you function names in profiling reports. This is the only reason this file is needed. So let's go ahead and record the CPU behavior of this process. I'm going to do a perf record. I will ask for stack traces. I will record 997 samples per second because that's what I like. You can configure the number of samples as you like to control overhead, essentially. And I will attach to the specific process, because I'm not interested in system-wide CPU information, just that specific application. So this is running now and collecting, essentially, until I hit Control-C or until the process terminates. You'll notice the process keeps running. It's not affected. It's not like you had to restart it to profile. This is perfectly suitable for production use. And perf tells me that 9,847 samples were generated. So perf actually sampled the CPU almost 10,000 times and wrote down every single sample with a stack trace. Now, there's multiple ways we could visualize this information, but a flame graph is easiest. So I'm going to skip a little ahead and a couple of demo steps and just show you a ready-made flame graph of the same application that I generated in advance. There's multiple ways to generate flame graphs. The easiest one is using a Perl script, which takes in the perf file and just spits out this beautiful, well, relatively beautiful diagram. So recall that the wider something is, the more prominent it is. This is how you read this thing. You look at the widest things. So looking at the right first, because that's not the widest thing, but it's interesting, you can see some GC code over here. So GC1, for example, is a function in the garbage collector, in the CLR garbage collector. And you can see from the tooltip, it was responsible, in this particular profile, it was responsible for 20% of the CPU samples. So 20% of the time I was actually doing GC. Looking at the main part of the flame graph, the widest part, there's functions here like main and fetch and then process result. So maybe it's not the HTTP requests taking lots of CPU time, but it looks like I have a function called process result, which is taking 60% of my CPU time. And what is it doing? I can zoom in only on that particular function and its descendants. And then you can see on the left, I have a lot of string allocations. So I'm allocating lots of large strings, and these are stacks inside the garbage collector. I also have this taking a lot of time, like 40% of my time is mem move avx unaligned erms. This is actually a function that's clearing out memory. That's what it's doing. It's placing zeros in memory. So that was also called a lot, because I'm doing lots of allocations. And finally, there's also a little flame over here, which I don't know if it's significant, but I could touch it and then see exactly what's happening here. You'll notice the stacks go all the way into the kernel, not just managed code, not just CLR code, but all the way into the Linux kernel with functions like sysmprotect, which is a Linux system call. So we have, and let me just unzoom, we have a visualization of the way this application is spending CPU time. And the flame graph itself is platform independent. Of course, you could generate a flame graph from Windows data, from Linux data, from macOS data. It's just a visualization method for seeing where my application is hitting lots of stack traces of a certain event. In that case, the event was CPU usage, but you could generate flame graphs of other kinds of events as well. So we have determined that this app is, as part of processing results, is allocating lots of memory, and there's also lots of garbage collection going on in the background. So a little later, we will come back to that and try to understand where these garbage collections are coming from exactly, which types are being allocated. So we'll come back to the memory aspect of this application. So far, we just looked at the CPU part. So let's see if I haven't missed anything. PERF record. These are just screenshots of the demo I've just shown you, and the flame graph we just looked at. So what we did so far was look at the perf way of doing things. And again, just to remind you, we ran perf, and then we got a file, perf.data, which had almost 10,000 samples, CPU samples inside. Now, that's actually not so bad. It's 2 megabytes of data from, I guess, about 10 seconds of running time. So I could imagine leaving this on for like 10 minutes, maybe half an hour, getting a few gigabytes of data, then analyzing them. It's actually still kind of sort of feasible. But for higher frequency events, like if I tried to collect using perf file accesses or network events, and I had like millions of events per second, the file would be pretty big, pretty unmanageable, I'd say, unopenable by any standard tool. So this is where an alternative Linux kernel technology comes in for collecting performance information. This is not covered by the official tools, like the perf collect tool I mentioned earlier. It uses perf exclusively, but once you know what's happening under the covers, you can obviously use other tools as well. So we're going to use that new underlying kernel technology called BPF. And I could spend like 2 hours talking about BPF itself and where it came from and what it can do for us. But in the context of .NET performance investigations on Linux, you should know that BPF is often an alternative for getting lower overhead data, for getting lower overhead performance investigations when the rate of events is high. So if you're tracing a system with lots of networking and you're interested in networking events, perf might generate lots and lots of data, and BPF might be a lower overhead. Or if you are sampling CPU usage and you have a large number of cores and you're doing high-frequency sampling, you will again get huge files, and BPF can be an alternative that generates lots smaller results. So the way BPF basically works for us, as opposed to perf, is that it does the aggregation in the kernel. Instead of generating a perf.data file, which we have to then aggregate in user space by running some sort of script, what happens with BPF is that the aggregation is happening in the kernel. So just to explain what I mean by aggregation very briefly, if you have 1 million stacks which are all the same, I have 1 million stacks in the exact same function spending CPU, then if you use the perf approach, you have to record every single call stack to the file. So you have 1 million records with exactly the same call stack in your file, and then you can do an aggregation in user space. This is also how ETW on Windows works. This is how most profilers actually work. They record every single call stack, and they do the aggregation offline. With BPF, you do the aggregation online. You do not record every single call stack. You just know it's the same call stack you've already seen, and you increment the counter. Oh, okay, so I've seen this call stack 1 million times. Now I've seen this call stack 1 million times plus 1. That's sort of what you do in terms of aggregation. So BPF-based tools are, by default, more efficient. The question is if this efficiency is actually important for you, like what the overhead is in the first place, so you can improve it. We're not going to be using BPF directly anyway. We will be using a front end, a bunch of Python scripts on top of BPF, which is called BCC. This is an open source project with a lot of contributors from different places, including Facebook and Netflix, and I've written a couple of these tools also. And they are basically wrappers on top of the underlying kernel features, which are easier to use because it's just Python scripts that you have to run with certain parameters. And this can be used for .NET investigations, absolutely, and I'll show you a couple of examples. The only reason why you wouldn't be using BPF always, just by default, is that it requires a fairly recent kernel. It's only supported, the things we'll be doing are only supported in kernel 4.4 or so, which is what you have in Ubuntu 16, Fedora 24, so recent Linux distributions will have that, but if you try to run these tools on like CentOS 6 or something, you will need to upgrade your kernel, and then it's a little trickier. So here are some of the tools that open up once you also start using BCC. There's tools here for low-level stuff like file system and disk and network, and there's also tools for managed languages. For example, there's a tool we could use for .NET called UGC, which traces garbage collections. Whenever there's a garbage collection, it prints out a message and the time it took. So we have tools very high level for specific runtimes and even databases for tracing database queries. And we have tools on the very lower levels of the system, including even CPU events in the picture. So these are all part of the same package, and I obviously encourage you to try them, even if you're not doing .NET Core on Linux, but rather something else on Linux instead. So let's see some examples of tracing. I'm going to do some of these as screenshots just to save us a little time. So what happens here on the left is that I have my buggy application run in a slightly different scenario. And here it's just kind of not starting properly. It keeps printing out opening configuration file, and doesn't make any visible progress. Now, obviously, there's a bunch of tools we could run now. Maybe we could look at the log file, but the log file doesn't say anything. Like, this is the only information I have. Opening configuration file, good luck with that. So in this kind of case, what is often helpful is to use a workload characterization tool that would look at this process and tell you what kinds of things it's doing, like what kind of activity is happening. So it could be a high-level tool, like is this using lots of CPU, yes or no? Or it could be slightly more specific, and we have a tool called syscount, which is designed for looking at system calls. I can attach it to a process, and it will display all the system calls this process is making, aggregated by number. So I can see in the output here that this process, has made 4 open syscalls and 10 futex syscalls and so on. So every system call, every interaction between user and kernel space is counted. Now, suppose I am interested specifically in these open syscalls. There is a dedicated tool called OpenSnoop, which we could run to get an output of all the opens, all the files we are trying to open in that application, which kind of makes sense because we keep getting errors about opening a configuration file. And the output just tells us that, yeah, well, we are trying repeatedly to open this file called etcbuggy.conf, and the file does not exist. Or anyway, there's an error opening the file because in the file descriptor column, I get -1. So the open call is actually failing. So just by looking at the process, figuring out which system calls it's making, and then tracing specific ones, tracing opens, we are able to understand why this process is failing to initialize and what file it is looking for. And then maybe if I create that file, it's actually going to start up. Now, this is not .NET specific. This could have been done exactly the same way for a Java app, or for a C++ app, or for a Python app. So let's switch to something that's more .NET specific. And this I'm going to do live. So remember this fetch application? It's actually still running, still fetching apple.com and burning lots of CPU. And we already know from the flame graph that we had lots of garbage collections from the info we generated previously. So let's switch to actually figuring out how many. So the question I want to answer now, how many garbage collections is this process having? Now, on Windows, it would actually be pretty easy. Like if you search Stack Overflow, you'd probably find 10,005 answers saying you should use Windows performance counters, and there's a Windows performance counters called GC collections under .NET CLR memory, and you can see this in like 5 seconds. Not so much on Linux, and there's two general approaches we could take. One is going to use runtime events, and we'll come back to that. The other option is just saying, okay, well, this is all happening inside the CLR. The CLR has a bunch of functions for GC, like a bunch of C++ functions that do garbage collections. Let's just trace those functions. And Linux actually has tools that enable me to attach to any arbitrary user space function and trace its invocation. So here's how it's going to work. I'm just going to use a command I typed in previously, and you'll shortly see why. So this is the command I'm going to run. So the tool itself is called funcount, and it's not actually a very difficult tool. You just give it a pattern, and it will trace all the functions matching that pattern. The only hard part here is the path to libcore_clr. Libcore_clr is just the main CLR component. This is where the garbage collector lives. And because this is a standalone .NET app, I've used .NET Publish to package it. It doesn't depend on the main shared .NET installation anymore. It's all just local. And so this is just the file I can ship with my app, and that's what I'm using. So libcore_clr, and I'm interested in all the functions that have this pattern in them. So anything that has garbage collect inside. So I just have to run it from the right folder, though. So let me go to .NET Buggy and run it from here. No, it's not here. It's over here. No functions matched by pattern garbage collect. What, seriously? Oh, and the star at the end. Okay, so 14 functions actually have garbage collect in their name, and we are now live tracing all of them. This is kind of like a debugger, but a million times more efficient. And once I hit Control-C, I get a summary of how many times each function was invoked. Now, this looks very scary because these are mangled C++ function names, and you don't see the actual class name nicely, but I could take this thing and pass it through a command line tool called cppfilt, and then you see it's actually a pretty reasonable name. It's a function called garbage collect generation, which takes an integer, which is probably the generation to collect, and an enum called gcreason. So this is very similar to the managed API. So now I want to know who is calling that function in my process, like where are garbage collections being caused. So for this, we can use a different tool, and again, I'm just using a command I previously typed called stack count. And stack count takes very similar arguments, except I give it a very specific function, like trace this function and tell me who calls that function. Kind of like a debugger, but again, in a much more efficient package. So if I run this, it's tracing until I hit Control-C. And finally, here's the interesting part. The output has call stacks in my application, and the number you see on the bottom is the number of times this call stack appeared. So 3,988 times, that function was called by the following call stack. Now, this is all not interesting. This is just C++ code inside the CLR, but it is getting interesting over here. So this is my app, this is process result, this is allocate string. Now, we kind of knew this already because we cheated and looked at the flame graph before, but we now know where the garbage collections are being caused. And so in lots of the cases anyway, in 3,988 cases in the recording I've made, they are caused by this particular place in my application. This could be a lot easier. Like this definitely could be simplified, but unfortunately, currently with the tools we have for .NET Core on Linux, this is kind of the way things work. You have to mash different tools together and usually get something functional, but at the cost of having to kind of redevelop the whole process yourself. So I've done some of the work, and I've also documented some of these things, but it is still a little tricky. I want to show you a couple of examples before we move to dumps for the end. I want to show you a couple of examples based on the actual runtime events that are part of the CLR. So this is moving more to the official side of things. Turns out, again, that the CLR itself has events built in for different interesting things that are happening. Garbage collections, exceptions, assembly loads, JIT compilation, a bunch of different events have in the runtime a dedicated location that would print a message, essentially, where that event occurs. Now, the way this works on Windows is using ETW, event tracing for Windows. Linux doesn't have event tracing for Windows, so instead, Microsoft opted to use LTTNG. LTTNG is Linux tracing toolkit, next generation, I think. It's basically a library for tracing, for emitting log messages on Linux systems. It's fairly efficient, and the general infrastructure is that there is a kernel component which can attach to different events and then emit those to either a file which can be analyzed later or a memory buffer that can be analyzed in real time. Now, if you're getting a deja vu with the PERF slide, it's for a good reason, because it's essentially the same architecture. You have a kernel component which aggregates events and then can push them to either a file or a live memory buffer for consumption, except this is what they chose to use instead of PERF. There's actually lots of additional logging frameworks like this. So how do you use this thing, and what can you do? First, in terms of events, so we're not going to be interested in kernel events for this because we already have PERF. What we will be interested in is user space events, which are part of the CLR. So you do need to get a list of the different events you can attach to. This is not very easy, but you can read the source code. So the core CLR source code on GitHub has a list of all the different events. So exceptions and GC and JIT compilation, all the things I mentioned, you can take a look at the source and find them there. And then here's what the workflow actually looks like. So some I'm going to do as a screenshot, some as a live demo, because there's just a lot of pointless commands to type. So basically, LTTNG comes with a command line helper called LTTNG, which you use to create a recording session, to add the interesting events you care about, and then to get the actual file, the actual recording. So you can see here, we create a trace session. We add a few context values, such as the process ID and the process name, so we get those as part of the trace as well. We enable all the .NET runtime events, starting with exception. And we also enable all the .NET runtime events, starting with GC. And then our application starts logging as soon as we call LTTNG start. So this still happens in parallel with the application. You don't have to restart the application. You don't have to do anything invasive. The app is running, and in the background, you run these commands to get a recording of all these different events. And then finally, you can do stop and destroy to finalize the recording. And let's see what the end result actually looks like. So I'm going to resize this a lot. There's a tool called BabelTrace, which is one of the tools for parsing LTTNG recordings. And I can point this thing to my trace file under LTTNG traces, my trace. If I just do that, it's going to print lots and lots of screens full of events. Each line here is a runtime event, such as you see here, GC sampled allocation high. This is one of the events the CLR can emit. Now, this isn't particularly interesting. Let's look for exception events in this output, for example. So I'm just going to ask for the first two. These are the first two exception events in this trace. So you see exception thrown. The exception happened in the buggy process. The exception type was HTTP curl exception. I had the exception message saying couldn't resolve host name. So it's actually giving me the exception details, as you could see in the exception object. The one thing it's not giving me is the stack trace, which is a pretty valuable thing for an exception to have. But unfortunately, LTTNG out of the box does not support stack traces. So like LTTNG as a choice for a logging framework assumes you don't want stack traces, which is, again, kind of weird for exception events, but probably sort of okay for most other events you'd want to emit. So let's take a look at something else. Instead of exception, let's take a look at GC start events. So here are a couple. GC start v2, that's the actual event name. And the details here are actually a little more cryptic. So what is the count? What is the depth? What is the reason? We don't really know. We'd have to go back to the source to understand. But obviously, we could build tools on top of this. So this is the underlying infrastructure. It's fairly low level, but we could get a listing of all these different events and build tools on top. One very, very simple example of a tool that you can build on top is just a one-liner shell command. So what I did here is I recorded GC allocation events, so basically memory allocations events from the .NET process. And then I sorted and removed duplicates and counted the number of appearances. And so at the end, I get as output the number of times I allocated objects of a certain type. Now, this is sampled, so it doesn't represent all my allocations. It represents a sample of my allocations, kind of like CPU sampling. But it's, again, illustrative of the things that you can do. We could grab all the runtime events, and then we could build processing pipelines on top of those. And I say we have to build because that's what we have to do. It's not something you get magically out of the box as part of a tool. You do have to build this on top of the infrastructure I'm showing you here. It's all a story of how you build your own performance tools, essentially. So one final thing I want to talk about, and then if you have any questions, is core dumps. And how to analyze crash dumps, core dumps of .NET applications in the field. This could warrant its own talk, but I'm going to give you the highlights. So first of all, just to make sure we all know, a core dump is a snapshot of a running process. So you have a process running, and then maybe it crashes. You want it to be captured to a file so you can analyze the reason for the crash later. So that's what a core dump is. You come to a running process, you suspend it for a second, you save the whole thing to a file, and then the process can keep running. If it actually had an exception and crashes, then it doesn't keep running, but at least you have a snapshot of where it was when it crashed. So this is the general idea. How do you generate core dumps on Linux? This is not .NET specific, again. There's a file that you set in order to tell the system to generate core dumps at all. And this can actually be configured to not write out a file, but to run an application where there's a crash. There's a lot of stuff behind this file. But you can tell the system to generate a core dump when a process crashes. There's a limit on the maximum core file size, which you would sometimes have to increase, because it sometimes starts at 0, which means you don't get a core dump file. And finally, once you do that, you will get core dumps for crashes. If you want to generate a core dump on demand, like maybe your application server is stuck and you want to see what it's doing, then you will also want the gcore tool, which comes with GDB, and you can point that to a process and get a dump file on demand, get a core dump at that instant in time. Now, what do you actually do with this? So core dumps, you can analyze exclusively using lldb. On Windows, you can actually open crash dumps with Visual Studio. But you cannot take a crash dump from Linux and open it in Visual Studio. This is not supported. So you need to do this on your Linux system, and you need to use specifically lldb, not GDB, because GDB doesn't have a plugin for .NET code. Now, once you actually open lldb, I'm going to show you what happens. So I have a core dump of a crashing application. I'm going to show you maybe the crash for a second here. This is what the crash looks like. When the application crashes, it's a console app, so it prints out, I had an application exception, and I get a call stack. I get the crashing call stack right here. Now, if you've worked with TPL before, you might be able to recognize this. This is not the original crashing stack trace. This is what happens when you run a task in a different thread, and there's an exception in that task, and you didn't process that exception, and then when the task object is finalized, it will throw an exception for you, telling you that you had an unhandled exception in the task, but not actually giving you the call stack of that other exception that happened. So this is a pretty nasty situation. But fortunately, we had dump files configured, so we had a core dump for this scenario. So here I'm opening that core dump using lldb. There's nothing particularly fancy in this command line. This is just the path to my application, and this is the path to the core dump file. So lldb spits out a lot of output. I'm going to clear the screen. Now, the first thing I want to ask for is the call stack. Tell me where we crashed, like what the exception stack trace was. There's a command for this, bt, backtrace. Here's what it says. So, like, this is fun, and this is great, but this is my C# code. We are familiar with this issue. Something needs to give debugging information for these addresses. We need to translate them to function names. Now, we might have a perf map file, but lldb cannot use perf map files. Perf map files are for perf. lldb cannot use perf map files. So what we need to do is essentially not use the underlying debugger, but instead load a plugin which ships with .NET Core. And that's actually pretty much the same story on Windows. If you use WinDBG on Windows to analyze crash dumps, you need the SOS debugger extension, which some of you might have heard about and used before. On Linux, it's the same story. You need a plugin. You need the SOS plugin for lldb in order to inspect .NET crash dumps. So the plugin is just part of the .NET Core distribution. So here I am loading it. It's called libsos plugin SO. And it also needs to take the path to the CLR. For some reason, it can't detect it, whatever. We've done this, got it out of the way. Now we get a bunch of additional commands in the debugger which are coming from that plugin. So one example of this would be, for example, the threads command. The threads command tells me what my managed threads are, my .NET threads, not all my application threads. And it shows me here that my first thread, this one here, in the exception column, it has an application exception. This is the exception we have already seen. We know about this guy. So let's take a look at the exception object from here. SOS has a command called print exception, which takes an exception object and prints its details. Now, this is the same as it is in WinDBG on Windows, which is at least one good thing about this. Now, as you recall, it prints out a pretty useless call stack. It tells me that I had an unobserved task exception. This is not the original exception call stack. This is just how it manifested. So I need to get like the inner exception somehow out of this thing, except it's not really there. So we're going to do it slightly differently. I want to switch to that thread and look at that thread's call stack. Maybe we'll figure out something from the call stack. So typically what you do is run the CLR stack command to get a stack trace, but then lldb, well, the plugin complains, unable to walk the stack, the current thread is not a managed thread. So if you look at the threads output again, the Linux thread ID for this thread is 957C, whereas the debugger here thinks it's 0. Because for some reason, again, you have to tell the plugin explicitly which Linux thread ID corresponds to the current thread in the debugger, which is insane because it already knows this, but you need to tell this anyway. So there's a command called set SOS thread ID, which takes the OS thread ID 957C and the debugger thread ID. Don't ask me why you need to do this, just know that you have to do this, and I wrote a script that actually automates this, but in any case, once you have done that, you can actually run CLR stack and get the managed call stack for that current thread, which is the same thing we saw in the exception message. So why am I even doing this? Because the publish unobserved task exception method and also my function here, handle unhandled exceptions, takes an event args object which contains the original exception information. So my plan right now is to glean that original exception out of there. And the way I'm going to do that is ask for parameters to be displayed. And then you'll see here, it tells me that my function handle unhandled exception takes an event args which has this value. So at this point, I'm going to ask the debugger to display this object. Again, these are the same commands from Windows SOS, except if you don't use Windows SOS, it doesn't help a lot, but it is the same commands. And notice what happens here. The unobserved task exception event args inside has the original exception. Now, once we have that, we could maybe hope to see the original exception, sorry, print exception, not dump exception. We could hope to see the original exception, but it's an aggregate exception. And the TPL aggregate exception doesn't so easily give up what the actual exception was. So you need to look at the object instead. Let's do SOS dump obj and print out that aggregate exception object we are printing this time. The aggregate exception object has a list of inner exceptions inside. So you can take that list, and dump that. And inside the list, there's an array of exceptions. So now we could dump that array. And in the array, there's just one element. There's just one exception we're hunting for, which is here. And assuming it is an exception, we will get the original exception message and its call stack. So it turns out we actually had an invalid operation exception in a background task, and this is the source code in my process which caused that exception in a background task, and that was wrapped by the aggregate exception business, which was so tricky to figure out. But I wanted to show you an actual real example of why you would need to analyze the core dump, because the original exception message was totally useless, and it didn't point to the actual place in my source where the exception occurred. Visual Studio would have done this for you in like 3 seconds. You would click, 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 and you would get to the original exception object. This is slightly more complicated, but this is the only alternative for Linux. This is the only way you can analyze core dumps of .NET Core processes on Linux. So if I tell you that the whole diagnostic story is not like 100% super baked and complete yet, I hope you understand why. So let's wrap up. This is just a set of screenshots of the whole walking through objects I've just shown you, so you could replicate this later. I have a checklist slide here, which is just for your reference, that shows all the things you would need to configure and set up in order to be able to do this diagnostics on your own machine. Some of this is needed for performance investigations, some of this is needed for tracing, and some of this is needed for core dump analysis. But if you don't go through these steps ahead of time, you would not be able to come to a running .NET Core app and get out all the information I was able to show you in the demos. So there's actually some preparation required, which I skipped to make this a little shorter. In terms of what we covered, just to make sure we really saw it all, we profiled CPU behavior in .NET Core applications using PERF and flame graphs. We visualized, again, the stack traces we got and saw nicely in a nice diagram illustration where our application was spending lots of time on the CPU. We used Linux tracing tools such as PERF and BCC to look at .NET Core applications, and that works. I mean, no reason why standard Linux tools wouldn't work for .NET Core processes. We looked at .NET Core runtime events like GCs and exceptions, which are emitted using LTTNG. So we have to use the LTTNG toolset to look at those. And finally, we looked at dump generation and analysis, which requires lldb and the SOS plugin and a bunch of additional commands that you have to remember. This whole thing is painful, and again, there's lots of room for improvement here. I hoped to see lots of changes in .NET Core 2.0, but there weren't any significant changes. There's a lot of work in progress, but if you are currently deploying .NET Core to production, or if you're planning to, you should be advised about the meaning of doing performance investigation on those systems. Trivial issues would be trivial, and the hard things will be very, very hard because the tools are in this sort of state. I have a bunch of references for you to look at later, including some of my own blog posts. You can find this whole thing in my slides, and the demo application I've used is up on GitHub as well, so you can replicate some of these experiments if you would like. If you have any questions, if you're interested in .NET Core diagnostics at all, please catch me later. I'm out of time, but there's a longer break now, I think, so we can absolutely have a chat if you'd like. And I hope you enjoy the rest of NDC. Thank you very, very much for coming. Thank you.